interface. Once you drill the reservoir section, which is the source, right, where is their hydrocarbons is accumulated, then you drill to that section, and then the completion is the means of bringing hydrocarbons to the surface in a safe and efficient manner. Completion is a mix of basically what you need to, as a completion engineer, you should have a background that you understand the physics, chemistry, mathematics for the calculations, general engineering. You need to also have an understanding of geology, hydraulics, because you're moving lots of fluids, interfaces, material science, and you should also have some of the well side experience. Okay, well engineering in general, there is a drilling, completion, and intervention. They work together. Basically, drilling, they complete the well drilling to the target zone to make sure that we can safely design the completion that is required. And the intervention is basically once you put the well on production, any kind of remediation work, anything happened in the well that you need to fix, that's the intervention engineering job. And they're all connected to each other, because if you haven't properly drilled a well and designed it, then the future intervention future intervention jobs can be problematic. That's why you have to consider, when you drill a well, you have to consider what kind of completion design will be implemented in that well, and what can be the potential intervention jobs that your well design should allow this in the future. This is like a general picture of the well. Like it's very it's not for scale, and it's also for a general rule, like deviated or horizontal well in 90 degree in the reservoir section. And then this is the well when you drill to the reservoir section. This is conductor casing. It's 20-inch or anything, it can be 30-inch. Mainly it can be cemented to the surface, or it can be hammered down or drilled to the surface. Then you run the surface casing, which is smaller, and then you run the intermediate casing and production casing. The one main rule you need to basically keep in your mind, that when you drill a well, it comes from bottom to top. It doesn't come from top to bottom. I mean the design wise, okay? Because when you're like a reservoir engineer or subsurface team decides that they're gonna drill to that target, they need a well to that target, and they need to produce some certain amount of hydrocarbon. You have to start from bottom. Okay, what's gonna be my tubulars or to be run in that well, and then based on the tubulars, you need to design the production casing. Tubulars, I mean the completion string, right? It includes tubing, it includes different type of equipment as well. I'll talk you about that in the next slides. And then you, from the top down, from the bottom up, you design your well and construct based on that. If you look at to the next slide, you see the, sorry for that, illustrating down, but the completion engineer is on the heart of the, quickly. Completion is engineer. If you see, this is the illustration from Jonathan Bellerby book I can share with you, which is a well completion design book. It's in the heart, and why this picture shows the completion engineering in the middle, because some of the engineerings they can work on their own, for example geologist or the service sector, but you have to be in the middle to understand what is your reservoir looks like. You can understand what kind of completion design you're gonna implement. You have to understand the commercial as well, because of the cost associated with the well design. Metallurgy, what kind of metallurgy you need to run based on the fluids, and then the requirement. And then you have to also manage to have an understanding on the management, to the people management, project management, all these things. Service sector, because it's related to other engineering as well. That you cannot do everything on by own. You have to have a service sector's support as well. Facilities, because your well has to be tied into the facilities, need to be connected to the facilities. You have to have a understanding on that as well. Geologists, petrophysicists, that you understand the rock types, you understand the physics of the rock, and of course the drilling team as well. We work very close with the drilling team. As I said in the previous slide, that to have a better and good design of well, you have to have a good hole and then good cased hole that you can run your completion. If you move to the next slide, that talks on the what's completion depends on. Basically, when you design your completion, it depends on the reservoir parameter, what's gonna be the pressure, temperature, and production profile. If there is, what's gonna be the water cut. You have to understand the rock characteristics. Whether it is exploration well or appraisal well. Basically, you have drilling the first well in the region, or there are some wells you have to appraise the reservoir. You have to understand what type of fluids you expect in the well, whether it is onshore or offshore facility, what kind of rig you're gonna run the completion. And you have to also understanding and also to evaluate what's gonna be your trajectory, what's gonna be the casing in the well, mud type, and then is there any risk of formation damaging. And it also depends on the facilities, because as I said, you have to connect your last stage of the well to the facilities. In a basic overview, completions are mainly divided into the reservoir completion, and which is the completion between the reservoir and the well, and then the upper completion, okay, which is reservoir completion. Sometimes we call also the lower completion, and the second part is the upper completion from the reservoir to the surface facilities. This is kind of like a completion, lower completion parts. It can be the barefoot. Soccer does this kind of well. It has been an old wells. Basically, after you set the production casing, you just drill the reservoir section and you keep it barefoot. There is nothing in the lower completion, or you can put the pre-drilled or slotted liner. Basically, it's kind of casing, but you don't cement behind, and you have a holes in it that the hydrocarbon can pass through it. And the next one is the cemented and perforated liner, that you run the liner cement behind and perforate to get a connection to the reservoir. And next one is the open hole sand control screens or gravel pack. I'll talk about that in more depths. And the other one is similar to the open hole gravel pack, but similar to the cemented and perforated, but at that stage, you run that screen inside and you pump the gravel in between the cased hole and the screen and inside the perforation tunnels as well. I don't see the chat box. If you see, allow me any questions raising, let me know. I can stop and try to answer. Okay.
Of course.
Okay, there should be two main reasons for sand production. Why I choose this part? That's one of the important part of the completion or lower completion, because if you don't choose the right reservoir or the lower completion, you're gonna have lots of problems at the surface, and you can even damage the facilities as well. For the sand production to happen, there should be two reasons, right? First of all, rock failure and enough rate to bring sand to surface. If you have rock failed and there is no rate, well stop, shut in, you won't have this issue, right? You won't have sand production. Or if you don't have rock failure, then that's not going to happen as well. These two rules had to happen at the same time, that you will have a sand production at surface. Consequently, or the result of the sand production is very undesired, right? Because you're gonna have lots of problems at the surface. You can lose the well, you can lose, as I said, facilities, damage the flow lines, and erode the lines as well. I have put a video here that which is good because they say the picture stocks 1,000 words. Then it will help you to understand what's the sand production. I mean the sand control to basically to keep the sand in the well. Basically, for not to have any sand production issues, you better keep the rock or underground. You're trying to consolidate it. You're trying to prevent it to come to the well at all, right? It's always to prevent the problem rather than to mitigate, right? You're trying to prevent that it doesn't happen rather than if it happens, and then you're trying to look at, okay, how can I solve it? This is the video from the BP school. I mean, old video. I'll put the video. Let me know if you don't hear the sound. I can exit the presentation mode and then come back again. Do you hear the sound or not?
No.
Okay, let me share it again. Okay, you should hear now.
Control in petroleum sand production and its control in petroleum operations. BP's objectives with this video are to explain why sand is often produced along with hydrocarbons in soft rock formations, and to illustrate the methods we employ to control this sand production. When we use the word completion in the oil field, we are referring to the activities in the wellbore after the drilling of the hole is finished that result in a producible well. We will consider 5 completion types. A cased and perforated completion in hard and soft formations. A standalone screen completion. An open hole gravel pack completion. A cased hole frac pack completion. And an expandable screen completion. It is important to understand how these 5 different completion types relate to sand production. For a cased and perforated completion, we begin with a well that has been drilled to total depth. The casing is lowered into the well and cemented in place. A tubing string is run into the well. The casing is perforated. The well is underbalanced and begins to flow. If the reservoir rock has sufficient strength, high flow rates can be achieved without sand production. On a granular scale, hydrocarbons flow into the pore spaces between the individual grains that make up the rock. The grains are cemented together by naturally occurring minerals. Therefore, the grains are not affected by the fluid flowing between them. Much of the hydrocarbons that are being produced today are contained in soft or low-strength rock formations. If we use the same cased and perforated technique we use in hard rock, sand grains may be produced along with the hydrocarbons when we flow the well. Generally, higher flow rates will result in more sand production. As in hard rock formations, hydrocarbons flow in the pore spaces between grains. Because the grains are held together poorly or not at all, individual grains can be easily stripped from the rock. Water production, which is common in petroleum operations, further reduces the bonding between grains and exacerbates sand production. Sand production has many undesirable effects. Erosion of the wellbore and surface equipment, fouling of production facilities, and in severe cases, wellbore plugging. Clearly, it is very important to control sand production. In regions where formation sand is fairly coarse, we often employ standalone screen completions. This is a fairly straightforward method for sand control. The casing is set and cemented at the top of the productive interval, rather than being run to total depth. A hole is then drilled through the productive interval below the casing. A sand control screen and installation assembly are run into the hole. The installation assembly is removed. Production tubing is run, and the well is placed on production. The formation is allowed to collapse against the screen. The screen holds back the formation sand as fluids flow through. In regions where formation sand is too fine to control directly with the screen, we employ open-hole gravel packs for sand control. As in the standalone screen completion, the casing is set and cemented at the top of the productive interval, and a hole is drilled through the productive interval below the casing. A sand control screen and installation assembly are run in the hole. Gravel, which is actually high-quality coarse sand, is pumped into the well where it fills the void between the screen and the drilled hole. The installation assembly is removed. The production tubing is run, and the well is placed on production. The gravel holds back the formation sand, the screen holds back the gravel, and the fluids are allowed to flow through. In some regions, most notably the Gulf of Mexico, cased hole frac packs are commonly used for sand control. The casing is run to total depth, cemented, then perforated, much like the cased and perforated completion. A sand control screen and installation assembly are run in the hole, much like the open hole gravel pack completion. Fluid is pumped into the well at high pressure, generating a fracture that extends outward from the wellbore. This fracture can extend as far as a few hundred feet from the wellbore. A material called proppant, which is nothing more than high-strength synthetic gravel, is pumped into the well where it fills the fracture, the perforations, and the void between the casing and the screen. The installation assembly is removed. The production tubing is run, and the well is placed on production. As in the open hole gravel pack, the proppant holds back the formation sand, the screen holds back the proppant, and the fluids are allowed to flow through. Expandable sand screens are a fairly recent innovation. A special expandable screen is run into the well along with a rotary expansion tool. The screen is pressed outward against the formation by the expansion tool. The expansion tool is removed. The production tubing is run, and the well is placed on production. The forced contact between the screen and the formation will often prevent rock failure where a standalone screen would not. In summary, with no sand control, a soft rock completion may produce sand along with the fluids, especially if these fluids include water. This detrimental sand production can be managed somewhat by careful control of pressure drawdown and flow rate. But the mechanical methods, standalone screen, open hole gravel pack, cased hole frac pack, and expandable sand screen, provide the highest achievable level of assurance against sand production in soft rock formations today.
Okay, that's the good video I found that can explain even better. Any questions you have up to now, or we can move?
Sand production and its
Okay, if no questions for now, when in the video as well was talking about the sand production, you see it in the surface, how bad is that? It can erode the surface lines, and it can be release of hydrocarbon to surface, or loss of the integrity of the facility, and loss of production, loss of, and then it will be reputational damage as well. This is another picture which shows the blockage of the flow lines. Basically, I guess it's a separator. If you have a high sand production, it can block the lines, and then it will affect your production rate, and again shut down your facility. This is also been shown in the video. Basically, you see here there is a screen, right, which acts like holds the gravel in place, and then there is a formation which holds the hold back by gravel. Okay, we run the screen into the well, and then we pump the gravel between the formation and screen to make sure that no formation sand will pass through the gravel and then will flow into the well. I mean, the no formation sand, they can be found very small formation sand, but the main formation sand will stay in the well. And then mainly the sand production issue is caused by the how much is that the reservoir formation is consolidated, how much drawdown, basically how much pressure differential you're creating inside the wellbore and between the reservoir pressure, how much is the reduction of the pore pressure, what's the viscosity of the reservoir fluid, and then how much water cut we have in the well. Before moving to upper completion, I would like to show you, let me stop presentation, how the screens and then gravel look like. I have the sample of screen with me here. Let me know if you can see. Okay, this is the screens you see in the. Okay, basically this is shroud, which is the outer part, allows like to not to damage any internal parts of the screen. This is the screen itself. You've seen in the slides. It's like a mesh. I have a sample of like this is the screen. You see, it has a special opening depending on the gravel size, right? And then it is this one is slip-on type. It's just slipped on the base pipe. If you look at from other cross section, this is the cut of the screen. Okay, you see there is a base pipe here, which is perforated, and this is the screen itself. Okay, and this is the this is basically shunt tubes, which is the transport tubes, and this is the pack-off tubes. When you pump the gravel, right? If you look at like that, let me do it. If you pump the gravel will come. That's your packer in the well, right? Will come and then pack all this around, but will not be able to pass through the screens because the screen opening is smaller than your gravel size. It will be hold all here, right? And then the fluid which carries the gravel will come through and then pass through inside and will go to the surface. Basically, when you prepare how you pump the gravel, you prepare a gelled fluid which has a high viscosity, can carry the propellant, and you pump into the well, right, with the gravel, as I said, and then the gravel stays in the well between. This is, imagine your formation between the formation and screen, and then the fluid will go in. Let me show you the gravel one as well. But this is, you can ask what is that one. In case you have any blockage here, you won't be able to pump the gravel through this annular. In that case, gravel will come inside these transport tubes, okay, and then will pass to the pack-off tubes, which are here, and then will fill the any gaps or the gaps in the wall. Okay, that's the general about the screens and gravel pack. That's the inside how they look like. There is a roads, and you can see the small openings. Probably you can see here. And the gravel itself looks like that. That's the gravel sample from the well we've pumped. Right, we took the surface samples. If you look at, let me try to do like that. Okay, you see this is small grains, which is finely sized, and then it's a special size gravel. Okay, and then it's mixed with the special fluid, as I said, which is high slurry viscous fluid that you can pump into the well. Okay, any questions before we move to the upper completions?
I have a question.
Yes, go ahead.
What happens if your screener prevents the flow of the oil into the tube? Let's say all
What
the
happens,
gaps.
sorry?
What happens if the sand screener prevents the flow of the oil into the tube due to the sand? Let's say the sand, all the gaps contains with the sand. For that reason, there isn't any flow into a tube. What should you do in this, let's say, happens?
You mean if the sand gravel, right? You know this gravel, the one I showed. This is the same. It's also the sand. It's the sand from the nature, but they are properly sized, right? That it's a bit detailed, but I'll try to explain. Like you choose this this sand gravel that you're gonna pump into the well based on your formation sand, right? And then you calculate what should be the size of that, the diameter, I mean. And then this screens, you basically try to put this sand that it will be, imagine it's here, you pumped it here. This one will hold the formation sand, and the screen will hold the gravel, right? If you haven't properly sized that, if you as if I understand your question right, then you will either plug your screens or you will plug your gravel, which is acting like a filter in medium. Then you will choke back the production. You will lose the production. The aim is to get as much production as you can, but not getting the sand formation sand into the well. Did I explain it correct? Did you get your answer, or you were asking something else?
Actually not. Let me explain Azari.
Aha.
Əgər sən skrinləri kum vasitəsilə tutulsa, yəni flowun qarşısını alsa, bu vəziyyətdə nə edirsiniz? Yəni nə eləməli injinlər?
Əgər gravel özü tutubsa, yoxsa yəni ki, suxurdan söhbət gedir?
Bəli, formation sanddan.
Okay, the question is if your formation sand plugs, right, this gravel, is that right? Or plugs the screens?
Plugs the screens.
Yes, then you have to, there is a different acid, mud acid, or different type of acid you pump into the well. You make sure that you solve this formation. But if it plugs, right, means you have issues in the operations. You have either choose the wrong type of gravel, wrong size gravel, or the screens that the formation sand will pass through this and then plug the screens. Okay, this is the failure of your design. Is that correct? Did you understand?
Yeah.
Basically,
okay. Understand.
Yes. I can share with you later on how you choose the diameter of the gravel. That's another like the subject, and how you choose the opening of the screens. Okay, you cannot put any screen into the well and pump into any sand into the well. Okay, you have to basically take the sample from formation, do the PST analysis, particle size distribution, find the diameter of the sand particles in the formation, choose your formation like gravel, which is the can be natural sand or can be any artificial, and then based on that you choose your screen size. Okay. And then probably you might have some. Yeah. Okay. Good. Any other questions before we move to slides?
I have one question, like how often do we need to replace these compression types, as it is highly prone to corrosion?
No, it shouldn't be. You design your well that it can last at least 15, 20, 25, even more. I mean, it should be when you design your well, you say, okay, what is gonna be my field life? Let's say 10 years, right? Then you say, I have to put the equipment in the place that it can be withstand to the corrosion, everything in the well, at least 15, 20 years, right? More than field life, that you don't get any issues. But it might be the issue because of the quality, or you haven't expected. Then you have to try to fix it. In this kind of scenario, it's difficult to fix it because you have open hole. You have to basically either remove. I mean, if production is placed, you have to plug the well, you have to sidetrack, or you have to plug and then try not to produce from the eroded part. Or you can put, like, if something in here damaged inside, you can put the patches internal, like a additional screen internally. That will be your control measure. Is that?
Thank you, sir.
Did I
Yes, I got it.
Okay. Okay. See no more questions. Let's move to the slides. Talk a bit more about upper completion as well.
I won't ask.
Okay, go ahead.
What's the filters shown? Can we service this completion tools into the well?
And with what?
Clean.
Sorry,
Serve, clean or change size into the well.
But this is, you remember this slide when, let me show, this is this one. You see, you have, you run into the well and you set it in the well that you aim not to change it, okay? Because if you change it, then you have to pull all the completion to surface and change it, okay? That's why you have to choose the right design that you will try not to pull it to the surface.
Okay.
Okay. Because it's very difficult to retrieve sand with the gravel. It had, I think they had a practice that they have removed it, but it's really difficult to move the screens, the packed, with gravel. You might not be able to retrieve it. Okay, let's talk a little bit about the upper completion. We have talked about the lower completion, which is the bottom part, which is directly connected to the reservoir, but there is also the upper part, which is the called upper completion, or upper completion string, which is comprises of the production tubing, additional production equipment, kind of packers, safety valves, chemical injection valves, electrical submersible pumps, and etc. And it's installed once the pumping operation and lower completion has been completed. You have set your lower completion and then you run the upper completion. That's the general, right? There are wells that there is no lower completion. For example, if you have a cased and perforated well, you just run the upper completion with packer and then you produce through the upper completion string. The key elements of the upper completion, it's tubing selection. I think Manish asked the question, very good question as well. Like, what's the tubing? You have to consider the life of the well. You have to also consider what is the surveillance, what kind of data I want to get from the well, its pressure, temperature, or the temperature across the well, which is also acquired by distributed temperature sensor. And then for the safety reasons, you can have a subsurface safety valve for controlling emergency cases, or uncontrolled fluid, you can close it. And then the surface part, wellhead or Christmas tree, or in Azerit they say fontana armatru, or the spool tree, that you can hang the tubing string, and then at the surface you can control the tubing flow, the production flow. Fluids wise, basically we run the completion into the well in mud environment, and then we displace well to the basically once you see this here, you run your screens and lower completion part with drill pipes and then inner string, and then you set it, right? You see in here, you set it in place, and then you displace well to the brine environment or the water-based fluid. And then after that, you can remove this internal part, and also you can remove this string from the well. I don't know why it shows. Okay, let me try to share like that. Do you see better? Because the bottom part was missing. These are the packers, right? Packers are the key element of which provides isolation, and then at the same time downhole anchoring. There are permanent packers that you set in the well. Only way you can have to cut or mill it down. There are retrieval, and there are also retrieval packer. Basically, you cut the mandrel or you just pull, or you do you shift the mandrel and then you can pull it from the well. There are sill boards and tubing mounted packers, and hydraulic set and mechanical set and hydrostatic set packers at the same time. If you look at the general schematic, this is also, as I said, the completion design book, or it's, I guess, from the Pack Pro the model. This is the gravel packer. It has a slips. You see bidirectional slips. It doesn't allow the string to move up or down, and there is a seal element, which is a rubber element, depending on the fluid type you have in the well, which prevents the fluid flow, and that's the main one. And this prevents the tubing movement. There is also the isolation packer in the open hole, which is the swell packer. It's also full rubber element if you want to isolate between the formation and tubing. Another part of the upper completion, there are the nipples, right? There are different type of landing the devices. For example, if you want to set any kind of plugs or any equipment in the well, then, or you want to put like a gauge in the well, or to plug the well that you don't want to produce from the well anymore. That, depending on that, you can put the sitting nipple, polish nipple, which you can sit and set any sealing element in the well. There is a no-go bottom one, because you see here the seal was here, and this is the no-go sits in here. There is a selective nipple that for special equipment, that there is this profile will allow you set special type of well. And this is the hydraulic nipple that you can activate with hydraulic lines at the surface. And this is the sliding sleeves. Basically, sliding sleeve is for providing the basic. If you don't want to do anything in the well, you want to have a full string, then you put it in the well, and then at some point you want to open the port, and then, for example, you want to produce from the selective zone, or you want to pump the well, the kill weight fluid, kill the well for the contingent operations, then you need to have this kind of things. You run the Slickline, you shift the sleeve. This is, I guess, up to open. This side you open, shift up to open, and then you have a circulation pass, and then if you don't need it, and then you shift down to close. Side pocket mandrels, it provides the unrestricted flow that if you need any kind of control device to be installed, or kind of gas lift valves or chemical injection valves, you see here, that's why they call the side pocket. You see, it looks like a pocket, and you have any equipment in this pocket, and it doesn't restrict the flow, right? If you don't have this, you're gonna restrict the inside, and then you're gonna restrict your production in the well. This is the different type of flapper valve. Basically, you see this one stops flow into the reservoir only. Basically, you don't want to create, if you have a damaging coolant, you don't want your fluid to be contaminated in the reservoir. It's in closed position. This is formation isolation valve, kind of ball valve. It can control the flow from the reservoir and into the reservoir. This is the flapper valve in open position, and this is the formation isolation valve or ball valve in the open position. Okay, this is closed, open positions. Another part of the upper completion, basically what type of the upper completions we have. This is from, I guess, production technology course from Heritage. This schematics, you see, this is a tubingless completion. There is no tubing. It's very rare. You pump, you produce through the casing, and this is tubing completion without packer. You can basically produce at the same time from the tubing and from the annulus. This is tubing completion with annulus packer. That you isolate the annulus, that you don't allow. This is very generic one and very often used design. And this is dual tubing completion with packers. You have different packers, and you produce this zone with the bottom tubing and this zone with upper tubing. this is how the spool tree looks like. This is on the left side. This is horizontal tree. You see production is on the side, but this is basically a vertical tree because the production comes through that and then goes like that. You can control because this, you see the valves, which are the inner and outer master valve, or lower and upper master valves, are in the horizontal valves are located in horizontally, and the vertical one located vertically. That's why they're called horizontal and vertical. This is more complex. This is more for platform that you can reduce the space, but the vertical ones are normally the heights are longer than the horizontal ones. And basically this gives you the tree gives you the access to the well. You can do different wireline operations. You have a plugs here, and you can do the production. You can pump the chemicals into the lines, through the lines to get the valves clean. They are the same configuration you can do with the vertical tree as well. Let's talk a little bit about the vertical tree. Sorry, we talked about vertical. Let's talk about a bit of the interventions. As I told in the beginning, interventions are mainly that if anything happens in the well, like after you put into the production, then you do the intervention that you can intervene and fix it as required. There are different intervention operations. Slickline, which is the wire or braided line, and then you basically run the downhole tools with the Slickline. It's more simpler. There is Wireline or E-line, which are the conveyance of the downhole tools with electrical line. I'll show in the next slides. There is an electrical conduit in between, and there is a coil tubing as well, which is a continuous welded tubular for conveying the tool string downhole, and at the same time you can circulate in the well. For the main aspects of the interventions is the surface control equipment at the surface, connection types, weight limitation, and weak point you have to consider when you do the intervention job in the well. This is the pressure control equipment, generally how it looks like. You see on the right side of the picture, that was a tree I showed you now, which is a vertical tree, and you have a Slickline BOP, you have a lubricators, and then you have basically the grease head and pack off. Basically, what you do with that, I'll try to generally explain with you. Once you have a well in the production, everything is okay. You need to do some kind of intervention job. Then you put this, you see here, anything above the tree connections, you build on top of your tree, and then you run your in that case, I would say E-line tools through that, and then through that into the well that you can fix anything. You can basically change anything in the well. You add the perforations. All that kind of operations are done with this intervention or E-line operations. This is general. You see how it looks like. You assemble the tool string into the lubricator and put on top of your BOP, because you're dealing with live well, right? The well is on the production. It's not like completion. Your well is dead. You're doing the live well interventions, and then you have to make sure that you have the barriers in the well, and you can basically run the BHA or tool string into the well with help of your wireline. This is the coil tubing. You see in the coil tubing there is a big reel, which is like a bigger drum, and then there is the coil tubing, welded tubular are coiled on top of it, inside it, and then when you this is your well, okay, you put all this in here, and then you run the coil tubing, which is a continuous pipe, into the well if you need to change it something, or if you need to pump, clean the sand, anything related with the coil tubing, and you perform with that, which is for onshore operations easier, but for offshore you have to consider the deck capacity, and you have to consider the rig up, which takes longer offshore as well. The limitations for different intervention operations. For Slickline, it's less time and it's easy to rig up. You can run the drift tools on, you can do any mechanical operations, you can do the jarring. It's just the gravity based, you just lower it down and it goes with own weight, but it is limited with inclination because it doesn't have any reels and nothing. That's why you might not be able to run in all the wells. You have to do the modeling to understand that you can run to the desired depths. And it has a risk of wire parting at well, and that is you can leave the BHA in the well. Interventions, again, what you do with Slickline, you run the plugs, any protection or isolation sleeves. If you need to run and retrieve the standing valves, which I talked about, like you put inside the nipple profile. You can also do the pulling dummy valves in the gas lift mandrel. You can also do the fishing operations as well. This is wireline or electric E-line. Where you see in the middle, you have a conduit, which is the electrical line, which allows you to send the electrical signals to the downhole tools that you can activate and do the different operations. It's also less time to rig up. It is compared to Slickline might be a bit longer, but compared with coil tubing, it's less time to rig up. It is electrical application. It is costly than if you compare with Slickline. You can real time read the data at surface, like the gamma ray or casing color, any kind of tools you want to run that, or you want to understand the production logging, the production of the different intervals, then you run the production logging. And then it also has a wire risks, and it has a risk of part stuck in the well. I've already talked about that. What you can do with the wireline or E-line, you can do the logging, you can do the plug setting, you can cut the pipe, recover, you can add the perforations, and then you can do the opening of the sleeves or do the fishing operations as well. Coil tubing, it is the coil tubing, you have to consider whether it is onshore or offshore. It is for the onshore rig up is quick, offshore is longer and more expensive as well. It is a continuous pipe. You don't need to make up any time. You can just by unreeling your reel and then run into the well. You can do more application compared to Slickline E-line. Any operations you do with Slickline and E-line, you can do that with coil tubing. It has a hydrostatic and electrical application, but you have to consider the burst and collapse of your coil and any stretches, buckling limits, and what is the tubing ID limitation as well, because it might be not be able to run because the coil tubing is bigger OD than the Slickline and E-line. What kind of operation you can do? You can do the gas lifting. Basically, you run into the well, you pump gas into the well, you produce from the well, and then come out of well. You can also do the fracturing and acid treatments. You can do the clean outs, cementing. You can do the scale removal, fishing, all kind of these services. Like you can do the gravel pack with coil tubing, and you can do vertical and horizontal underbalance drilling as well with coil tubing. I think that's all for about like completions, what the completion engineer do. I guess I managed to give you some background, what is completion general looks like, and what is the intervention. Do you have any questions regarding to the presentation I went through today, or anything that you have in your mind that you want to discuss with me.
I have a question like, can we generalize which type of formation is more prone to sand production, like sandstone or carbonate like this? Can we do a generalization like this?
Sorry, I couldn't hear the question.
Can we generalize which type of formation is more prone to sand production, carbonate or sandstone, or it basically depends on
Good
local
question.
parameter?
No, you cannot generalize, but you need to study. I didn't go in that deep, but if you have a formation, you have drilled that formation, right? Then you have to basically take the samples, do different tests, right? You can do the basically just the nail test or the Brunel test to understand the formation. How hard is the Can you hear me?
Yes.
Yeah, I think
Yes.
someone didn't like me, just removed me from the meeting. And then basically you need to do the more detailed study to understand the hardness of the, but maybe if you talked very general rule, but don't copy me on that, you can say sand formations are more prone to more weaker than the carbonate, right? But mainly you have to do that. There are lots of sand formations, they don't require sand control. You just do the perforations or barefoot. You have to do this study to understand. Did I explain that
Thank
right,
you, sir.
Manish? Okay. Any other questions from the audience? Okay, if no questions, then we can we call the meeting?
Okay. Zaur Bhai, it was really informative session. As SPE.Khazar University Student Chapter, we are really grateful for your amazing presentation. Thank you to everyone who came out to participate in today's session. And if you don't have any further question, we may conclude our session.